Have you ever looked up at the night sky and felt that profound sense of wonder? That quiet, humbling sense that we are just a small part of something infinitely larger, older, and more mysterious than we could ever truly comprehend. Out there, in the silent, overwhelming vastness of space, secrets are being whispered across billions of light-years messages that have traveled for eons, only to be captured by our antennas and decoded by our most brilliant minds. These aren't just random bursts of energy, they are cosmic puzzles, signals so strange and specific that they defy easy explanation, challenging everything we think we know about the universe and our place within it. For decades, astronomers and researchers have been listening, tuning into the faint whispers of the cosmos, and what they've discovered is both thrilling and deeply mysterious. From repeating patterns that echo with eerie precision to sudden, powerful bursts of energy that appear and vanish without a trace, these signals are the universe's way of reaching out, and we are only just beginning to understand what they might mean. Some suggest natural cosmic phenomena, others dare to wonder if we might be hearing something else entirely. Each signal is a story waiting to be told, a piece of a grand celestial narrative that speaks to the curiosity and ambition that define us as explorers. In this video, we're embarking on a journey to uncover 25 of the most enigmatic signals ever detected, cosmic messages that have captivated scientists, sparked endless debate, and fueled our collective imagination. Together, we'll explore where these signals come from, what makes them so baffling, and why they continue to inspire both awe and intense curiosity. This isn't just a list of anomalies, it's an invitation to join in one of humanity's greatest adventures, the search for meaning in the stars. So settle in, open your mind, and get ready to explore the mysterious, the unexplained, and the utterly extraordinary. Our journey into the cosmic unknown begins not in the distant past, but surprisingly recently, in the summer of 1977. At Ohio Wesleyan University's Big Ear radio telescope, a massive instrument designed to passively listen to the heavens, a volunteer researcher named Jerry Amon was engaged in the painstaking, methodical work of sifting through reams of data printouts. This was not a glamorous job, it was a slow, meticulous search for a needle in a galactic haystack. Day after day, the printouts were filled with columns of numbers and symbols representing the unremarkable, constant hiss of cosmic background noise. But on August 15th, everything changed. As Amon reviewed the data from just a few days prior, his eye caught something that made him stop dead. There on the perforated paper was a sequence of characters so startling that he circled it in red pen, and next to it simply wrote, "Wow, this was no ordinary blip." The signal, observed for 72 seconds, the exact duration the Big Ear telescope could focus on a fixed point in the sky, was overwhelmingly powerful. It was over 30 times stronger than the ambient noise of deep space. The alphanumeric code he circled, 6EQUJ5, was a specific notation used by the telescope's computer to represent the signal's intensity. Each character corresponds to a number. The numbers 1 through 9 were represented by themselves, but intensities from 10 upwards were denoted by letters. So the U in that sequence, that represented an unprecedented intensity level of 30. This wasn't just a signal, it was a shout in a universe everyone had assumed was silent. What made the WOW signal so compelling wasn't just its strength, but its frequency. It was detected at 1420 MHz, a frequency nestled in a protected band of the radio spectrum known as the hydrogen line. This is a frequency band that is naturally quiet, reserved internationally for astronomical research, because it's where the hydrogen that pervades the universe naturally emits. It's precisely the kind of frequency theorists had long suggested an advanced civilization might use to broadcast its presence, a cosmic hailing frequency easily distinguishable from the natural chatter of the cosmos. The signal also exhibited a telltale rise and fall in intensity. exactly as you would expect from a distant, point-like source passing through the narrow focus of a fixed radio telescope. It checked every single box for what a deliberate, intelligent extraterrestrial transmission might look like, and then it was gone. Despite numerous, extensive searches over the following decades, using increasingly sophisticated technology, the signal never repeated. It was a one-time event, a single, perfect cosmic syllable that has never been heard again. This profound silence is at the very heart of the mystery. Could it have been a natural phenomenon? Suggestions have ranged from a comet emitting hydrogen to a random burst from a passing satellite, but none of these explanations have ever fit the data perfectly. The comet theory, for instance, fell apart as no known comets were in that precise region of the sky on that date. The signal's unique characteristics have stubbornly resisted all conventional astronomical explanations for over 4 decades. It remains the white whale of SETI, the one that got away, a tantalizing, frustrating, and utterly captivating piece of evidence that we may not be alone. A ghost from the depths of space that called out just once as if to say, "I am here," and then vanished back into the eternal quiet. Yet for all its mystery, the WOW signal was just the opening act. If that was a single, shocking shout in the dark, then the next signal on our list is a whole chorus of cosmic whispers, each one more baffling than the last. We're talking about fast radio bursts, or FRB, discovered relatively recently in 2007. These events are exactly what their name implies: incredibly fast, incredibly powerful bursts of radio waves that originate from galaxies far, far beyond our own. Imagine a flash of energy so intense that it can outshine an entire sun, but a flash that lasts for less time than it takes you to blink, just a few thousandths of a second. That's an FRB. For that brief, brilliant moment, it releases more energy than our sun will emit over 80 years, and then, just like the WOW signal, it's gone. For years, astronomers debated whether these one-off events were even real or just some kind of terrestrial interference, a glitch in the data. But then, one FRB changed the entire game. That game changer is known as FRB 121102. In 2016, astronomers made a stunning announcement. This particular burst, which originated from a dwarf galaxy 3 billion light-years away, was repeating. Unlike the singular, fleeting nature of other bursts, this one would periodically flare up again from the exact same spot in the sky. This repetition was a monumental clue. It ruled out any kind of catastrophic, one-time-only event, like the collision and destruction of 2 ultra-dense stars. Whatever was causing this signal wasn't being destroyed in the process. It was surviving, and it was doing this over and over again. The discovery of a repeater sent theorists back to the drawing board. The leading natural explanation points to a specific type of neutron star called a magnetar. These are the universe's ultimate magnets, the collapsed cores of massive stars, possessing magnetic fields so unimaginably strong that they could strip the information from a credit card from halfway to the moon. The theory suggests that starquakes on the surface of a young, hyperactive magnetar could be slinging out these colossal bursts of energy. It's a compelling idea, and it fits for many of the one-off bursts we've detected. But for the repeaters, the story might be more complex. Some scientists have proposed that the source could be a magnetar orbiting a massive black hole, with the immense gravitational forces periodically triggering the burst. Others wonder if we're seeing the powerful jets from a highly active black hole itself. And then, of course, there's the more speculative yet utterly fascinating possibility. The signals are so intense, so focused, and in the case of the repeaters, so persistent that some have asked if we could be looking at evidence of alien technology. The idea is that a sufficiently advanced civilization might need a tremendous amount of energy to power interstellar light sails for their spacecraft. To push a massive vessel across the incredible distances between stars, you would need a truly colossal beacon, a focused radio transmitter of planetary or even stellar proportions. From our distant vantage point, the intermittent, incredibly powerful pulse of such a beam as it swept across the sky could look exactly like a fast radio burst. It's a hypothetical scenario, to be sure, but it's one that underscores just how strange and unexplained these signals truly are. They are not just cosmic curiosities, they are direct challenges to our understanding of physics, pushing the limits of what we believe is possible in the universe. But while the repeating bursts opened up a new world of possibilities, we have to rewind the clock to understand where this entire mystery began. The story of fast radio bursts doesn't start with a repeater. It starts with a single, monumental discovery made almost by accident. It was the year 2007, and astronomer Duncan Lorimer tasked one of his students with analyzing archival data from the Parkes radio telescope in Australia. The data was nearly a decade old, recorded back in 2001, and it was gathered while the telescope was observing the Magellanic Clouds, two small satellite galaxies orbiting our own Milky Way. Sifting through this old data was not considered a glamorous project. It was more like astronomical archaeology, but what they unearthed was nothing short of revolutionary. Buried in the recordings from July 24, 2001, was a single burst of radio waves so powerful and so brief that it defied all known classification. It lasted a mere 5 milliseconds, that's 5,000ths of a second, but in that unimaginably short blink of an eye, it released a staggering amount of energy. This event, now famously known as the Lorimer burst, was the very first fast radio burst ever identified. The discovery was met with intense skepticism. How could something so energetic, originating from so far beyond our galaxy, exist and then vanish without a trace? The signal was so extraordinary that many in the scientific community questioned if it was even real. The most obvious suspicion was that it was some form of local interference, a glitch from a microwave oven in the telescope's break room, a passing satellite, or even an anomaly in the data processing itself. For years, the Lorimer burst stood alone as a curious and unverified outlier. Confirming its cosmic origin was the real challenge. The key piece of evidence was something called dispersion. As radio waves travel across millions or billions of light years through the sparse plasma of intergalactic space, higher frequencies arrive at our telescopes slightly before the lower frequencies. This smearing effect is a telltale sign of a signal that has journeyed a great cosmic distance. By measuring this dispersion, astronomers can estimate just how far a signal has traveled. The dispersion measure for the Lorimer burst was immense, pointing to an origin far outside our Milky Way galaxy, a truly extragalactic event. This single enigmatic data point paved the way for a whole new field of astronomy. It was the proof of concept that such incredibly short, incredibly powerful phenomena could exist. Once astronomers knew what to look for, they began searching through other archival data sets from telescopes around the world. And they found them. More of these bizarre millisecond bursts were hiding in plain sight, previously dismissed as equipment errors or terrestrial noise. The Lorimer burst was the crack in the dam. Today, thanks to that initial discovery, hundreds of FRBs have been catalogued by dedicated observatories. We now know they are happening all the time, all across the sky. Some are one-off events, dramatic cosmic explosions that occur just once. Others, as we've seen, are repeaters, sending out their powerful signals over and over again from the same source. Each new detection adds another piece to the puzzle, helping scientists narrow down the possible causes, from magnetar flares to collisions between incredibly dense neutron stars. Duncan Lorimer's archival find didn't just identify a strange signal. It opened a new window onto the universe, revealing a side of the cosmos that is far more dynamic and violent than we had ever imagined. Just as the hunt for cosmic signals was moving into the digital age, a project emerged that turned the search into a global, collective effort. SETI at Home, launched in 1999, was a groundbreaking initiative. Instead of relying solely on giant radio dishes, it harnessed the unused processing power of millions of personal computers around the world. Volunteers would install a screensaver-like program that would quietly analyze chunks of radio telescope data whenever their machine was idle. It was a brilliant distributed computing project, creating a virtual supercomputer made up of countless everyday devices, all working together to sift through the cosmic static for a sign of intelligence. And in 2003, it seemed this digital army might have found something. The candidate signal was given the rather unassuming name SETI-02+14a. What made this signal instantly intriguing were its parameters. It was observed at a frequency of 1420.4 MHz, incredibly close to the hydrogen line, and by remarkable coincidence, very near the frequency of the legendary WOW signal. This is the cosmic watering hole, the quiet spot in the radio spectrum where many scientists speculate an advanced civilization might choose to broadcast. Furthermore, the signal appeared to exhibit drift, meaning its frequency seemed to change slightly over time. This is a key characteristic astronomers look for, as a signal from a planet orbiting a distant star would be subject to Doppler shift, its frequency wavering as the world moves toward and then away from us in its orbit. On the surface, SETI-02+14 seemed to tick all the boxes. However, this is where the story takes a turn from excitement to intense scientific debate. The signal was exceptionally weak, barely rising above the background noise. It was detected not once, but on 3 separate occasions from the same general area of space, a point near the constellation Pisces. But here's the crucial catch: each time it was heard, it was at a slightly different frequency. Proponents of the signal, being a genuine candidate, argued that this frequency drift could be explained if it originated from a planet with an unusually rapid orbit, perhaps circling its star every few days. The fact that it was observed multiple times, even weekly, suggested it wasn't just a random glitch. The skepticism, however, was loud and well-founded. Critics pointed out that the signal's incredibly faint nature and its shifting frequency made it far more likely to be the result of terrestrial interference. A stray radio signal bouncing around our own atmosphere, perhaps from a satellite or even a faulty piece of electronics on the ground, could easily mimic these characteristics. The other major point of contention was the location in the sky. The patch of space where SETI-02+14 originated is notably empty. There are no obvious stars, particularly no sun-like stars that we might consider good candidates for hosting life-bearing planets within 1,000 light-years of that point. It seemed to be a signal coming from nowhere. The ultimate test, as with all these mysteries, is repetition. If a signal is truly out there, we should be able to point our most powerful telescopes at those coordinates and hear it again, loud and clear. Despite numerous dedicated follow-up observations aiming precisely at the location of SETI-02+14a, the signal has never been heard again. It vanished as mysteriously as it appeared. This profound silence has led most of the scientific community to conclude that it was almost certainly a highly peculiar and persistent form of radio frequency interference that fooled the algorithm. It stands as a testament to both the promise and the immense challenges of SETI. It showed that our distributed processing approach could identify subtle anomalies, but it also served as a stark reminder of how many earthly signals we have to filter out in our quest to find something truly otherworldly. It remains a fascinating footnote, a ghost in the machine that sparked a brilliant debate about what we're really looking for and all the noise we have to ignore to find it. But if SETI-02+14 taught us about the challenge of faint signals, the next mystery on our list is a cosmic beacon that refused to be ignored, one that was impossible to miss because it was quite literally blotting out the light of a star. Our story shifts from radio telescopes to optical ones, specifically NASA Kepler Space Telescope. Kepler's mission was profound yet simple: to stare unblinkingly at a single patch of sky, monitoring the brightness of over 150,000 stars, hunting for the telltale, periodic dimming that would indicate an exoplanet passing in front of its host star. It was a factory for discovering new worlds, and its data was a treasure trove of predictable, repeating patterns. That is, until citizen scientists stumbled upon a star that broke all the rules. This star, known officially as KIC 8462852, but now famously called Tabbys-star after its lead investigator, Tabby, displayed a light curve unlike anything ever seen. Instead of the gentle, symmetrical, and predictable dips caused by planets, Tabby's star underwent wild, erratic, and devastating drops in brightness. We're not talking about a fraction of a percent. This star would dim by up to 22%. To put that in perspective, a Jupiter-sized planet passing in front of a Sun-like star would cause a dimming of only about 1%. Whatever was blocking Tabby's star was colossal, and it was doing so in a chaotic, unpredictable pattern. There were deep, sharp dips that lasted for days, followed by a gradual return to normal brightness. There was also a long-term, secular dimming trend observed over the century-old archival data, suggesting the star itself was getting fainter over a much longer timescale. The strangeness was so profound that all the natural explanations fell short. It couldn't be a planet. Nothing that big could cause such sharp, irregular dips. A cloud of comets was proposed, a swarm of millions of them breaking up and creating a thick, uneven debris field. But the energy required to vaporize that many comets to create the observed dust seemed implausibly high. A recent collision between planetary bodies could create a massive cloud of debris, but that would be a temporary event, and the dimming kept happening. The data was so baffling that astronomers, in a moment of brilliant and honest frustration, began to entertain a more extraordinary possibility. Could we be witnessing the construction of an alien megastructure? The concept, popularized by physicist Freeman Dyson, is known as a Dyson sphere, or more accurately, a Dyson swarm, a vast collection of energy capturing satellites or solar panels orbiting a star, built by a civilization with technology far beyond our own to harness its entire energy output. Such a structure wouldn't be a solid shell but a messy, uneven swarm of objects, and as they passed in front of their star, they would cause exactly the kind of irregular, deep, and asymmetric dimming that Kepler observed. It was a hypothesis that perfectly fit the data, and it catapulted Tabby's star from an astronomical curiosity to a global sensation. Of course, extraordinary claims require extraordinary evidence, and the scientific community mobilized. The star became the most intensely studied in the sky, with astronomers across the world training every available instrument on it, from the infrared eyes of the Spitzer Space Telescope to the giant radio dishes of the Very Large Array. The key was to look at the dimming across different wavelengths of light. A solid object like an alien megastructure would block all wavelengths of light equally. However, if the dimming was caused by dust-fine particulate matter, it would block more blue light than red light, causing a telltale signature. The observations were conclusive. The dimming was much more pronounced in blue light than in red. This was the fingerprint of dust, not solid machinery. The current leading theory is that Tabby's star is surrounded by a massive, uneven ring of exoplanetary dust, likely the remnants of a shattered moon or a catastrophic planetary collision. This dust cloud is exceptionally thick and clumpy, accounting for the deep, irregular dips, and its slow inward spiral could explain the century-long dimming. Yet, even with this more natural explanation, puzzles remain. The precise origin of all this dust is still a mystery. How did it form, and what forces are shaping its bizarre behavior? Tabby's star may not house a construction project of a super-civilization, but it has revealed something almost as valuable, a new and violent type of planetary system, a place where cosmic demolition derbies are happening on an unimaginable scale. It stands as a powerful reminder that when we go looking for the extraordinary, we often find that nature itself is more creative and mysterious than we could have ever dreamed. While our gaze has often been fixed on distant, sun-like stars in the search for cosmic company, some of the most intriguing signals have come from the most common and often overlooked inhabitants of our galaxy, red dwarf stars. Smaller, cooler, and far more numerous than stars like our Sun, these faint embers were long dismissed as unlikely hosts for life-bearing worlds. But in 2017, a red dwarf just 11 light-years away, known as Ross 128, delivered a signal that forced everyone to reconsider. The story begins at the Arecibo Observatory in Puerto Rico, a legendary instrument whose massive dish was at the time one of the most powerful tools for listening to the cosmos. Astronomers were conducting a routine survey of nearby red dwarfs, studying their flares and magnetic activity when they picked up something utterly unexpected. For about 10 minutes, Ross 128 broadcast a strange, periodic signal that seemed to be anything but natural. The signal was what radio astronomers call quasi-periodic and broadband. This is a technical way of saying it wasn't a pure, steady tone, but a wide, sweeping series of pulses that repeated in a pattern. To the researchers analyzing the data, this was a massive red flag. Natural cosmic objects like pulsars or flaring stars tend to emit signals that are narrowband focused on a very specific frequency. This signal from Ross 128, however, was splashed across a wide range of frequencies, a characteristic that is hallmarks of human technology. Think about it, our own radios, satellites, and radar all broadcast across a broad swath of the spectrum to carry complex information. The signal from Ross 128 looked, for all intents and purposes, like it was artificial. The fact that it was coming from a nearby, stable star known to host at least one Earth-sized planet sent a jolt of excitement through the small team. Had they just stumbled upon a transmission from another world, the head of the project, Professor Abel Mendes from the University of Puerto Rico at Arecibo, did something quite extraordinary. Instead of quietly sitting on the data, he went public with the mystery. In a blog post, he laid out the 3 leading hypotheses, and the first one on his list was the most thrilling. It could be a signal from extraterrestrial intelligence. The other 2 possibilities were a new type of stellar flare from the red dwarf itself, or interference from a human-made satellite. The internet, of course, immediately seized on the first option, and the story went viral. The world was watching, waiting for an answer. This transparency, while risky, showcased the rigorous and self-correcting nature of scientific inquiry. The team knew the burden of proof was immense, and they embarked on a meticulous process of elimination to solve the puzzle. The first suspect was the star itself. They pointed other telescopes, including the powerful Green Bank telescope in West Virginia, back at Ross 128. If the signal was caused by some unprecedented stellar activity, it should still be there, or at least repeat. But the star was quiet, the signal was gone. Next, they considered if it could have originated from another astronomical object in the same field of view. Perhaps a distant quasar or a pulsar was hiding behind the star, but a thorough scan of the area revealed no such object that could produce a signal with those specific characteristics. One by one, the natural astronomical explanations were being crossed off the list. The evidence was increasingly pointing back toward Earth. The final and most crucial piece of the detective work involved the observatory itself. The team realized they hadn't just observed Ross 128 that day. The massive Arecibo dish had also been pointed at other celestial objects, and they began to review all the data from the entire session. That's when they found the smoking gun. The same strange, quasi-periodic broadband signal had also appeared when the telescope was aimed at several other stars. This was impossible. A signal from a single extraterrestrial source can't be in multiple places at once. The only logical conclusion was that the source was much, much closer. It was interference, but from what? The team meticulously triangulated the source. The culprit, they eventually concluded, was not one, but several geostationary satellites orbiting high above Earth. These satellites, which hang in a fixed position relative to our planet, can sometimes leak signals. As the massive Arecibo dish moved slowly across the sky to track Ross 128, it passed through the radio splash zone of these satellites just long enough to create that 10-minute burst of noise that perfectly mimicked what an artificial alien signal might look like. The resolution was a classic case of Occam's razor. The simplest explanation, satellite interference, turned out to be the correct one. While it was a disappointment for those hoping for first contact, the Ross 128 episode was a landmark moment for modern SETI. It demonstrated a new level of scientific rigor and public accountability. It showed how a potential false alarm can be systematically investigated and debunked through careful observation and logical deduction. This process, though it often leads to a dead end, is what makes the eventual discovery of a real signal all the more likely. It proves we are getting better and better at distinguishing the faint whispers of the cosmos from the overwhelming noise of our own technological civilization. This hunt for clarity in a cosmos filled with interference brings us to one of the most pivotal and humorous moments in the history of astronomy, a discovery that perfectly captures the tension between hope and rationality. In 1967, a young Cambridge graduate student named Jocelyn Bell Burnell was poring over miles of chart paper data from a new radio telescope she had helped build. The instrument was designed to study the twinkling of distant quasars, but as she meticulously scanned the endless lines of squiggles, she noticed something peculiar, a faint, repeating bit of scruff that didn't look like anything else. It was too rapid and too regular to be a quasar. Intrigued, she marked the section and moved on. Weeks later, using a faster recorder, she managed to capture the source of the scruff in stunning detail. It was a signal of breathtaking precision, a sharp pulse of radio waves that arrived every 1.337 seconds with a regularity that was more accurate than an atomic clock. For a small team of scientists, this was both electrifying and deeply puzzling. What in the universe could possibly produce such a perfectly timed, powerful signal? The possibilities seemed limited. It couldn't be a variable star, nothing that large could pulse that fast. It couldn't be terrestrial interference, as the signal kept perfect time with the stars, moving across the sky 4 minutes earlier each day as the Earth rotated. As they struggled to find a natural explanation, a more extraordinary idea began to surface. Perhaps they had truly found it. Perhaps this was a beacon. The signal's incredible regularity suggested an engineered source, not a natural one. Half-jokingly, they labeled the source LGM-1 in their notes, with LGM standing for Little Green Men. It was a placeholder name born from a mix of awe and bewilderment, a way to acknowledge the staggering possibility that they might be listening to a transmission from an intelligent civilization. The ethical dilemma was immense. Do they announce a potential discovery of extraterrestrial intelligence to the world, or do they hold back, searching for a more conventional answer and risk being accused of a cover-up? The team, led by Jocelyn's thesis advisor Anthony Hewish, decided on a path of extreme caution. They kept the discovery secret while they searched for other explanations and, crucially, for other similar signals. If it was a beacon from one civilization, surely there would be others out there. Before they could solve the mystery, a twist of fate forced their hand. A Cambridge administrator overheard talk of the discovery and leaked it to the press. Suddenly, headlines around the world were screaming about contact with Little Green Men, and the team was thrust into an international media frenzy they were completely unprepared for. The pressure was overwhelming, but the scientific process continued. It was Jocelyn Bell herself who ultimately found the key to the mystery. While the team was still grappling with LGM-1, she discovered a second, similar signal pulsing from a completely different part of the sky. Then she found a third, the odds of 3 separate alien civilizations all deciding to build incredibly powerful beacons and aim them at a tiny, insignificant planet like Earth were astronomically low. This was the clue they needed. The signals weren't messages, they were a new type of astronomical object. The source was natural, but it was unlike anything ever seen before. The team had discovered the first pulsar, a rapidly spinning neutron star, the ultra-dense, city-sized corpse of a massive star that had died in a supernova. As this cosmic cinder spins, its powerful magnetic field focuses beams of radio energy from its poles. Like a lighthouse, these beams sweep across the galaxy, and each time one flashes over the Earth, we detect a pulse. The incredible regularity was simply the rotation rate of this stellar corpse. The discovery was a monumental moment in science, earning a Nobel Prize for Anthony Hewish, though controversially not for Jocelyn Bell Burnell, whose critical role is now rightly celebrated. The story of LGM-1 is a beautiful lesson in scientific humility and rigor. It showcases the thrill of finding something completely unknown and the discipline required to not let excitement override evidence. It was a false alarm for SETI, but a triumphant alarm for physics, revealing a new and extreme class of object that continues to help us test the limits of gravity and matter. Those perfectly timed pulses were not a hello from another world, but they were a profound message, nonetheless, a testament to the universe's endless capacity to surprise us with natural wonders far stranger than we could have ever imagined. Just as the mystery of fast radio bursts began to deepen with the discovery of repeaters, 2 specific signals emerged that would push the boundaries of our understanding even further, offering tantalizing new clues to their origins. The first, FRB 1809-16, wasn't just another repeating burst. It was the first one we discovered that operated on a precise, predictable schedule. Imagine a cosmic alarm clock, one that goes off with incredible power at very specific intervals. This is exactly what astronomers witnessed from a galaxy 500 million light-years away. For 4 days, this source would unleash 1 or 2 bursts every hour. Then it would fall completely silent for 12 days. After that quiet period, the cycle would start all over again, creating a perfect 16-day rhythm. This regularity is a massive clue. In astronomy, a clock-like signal often points to an orbiting object. The leading theory suggests that the source of the burst, likely a magnetar, is in a long, elliptical orbit around another star or perhaps a black hole. For most of its orbit, it's quiet, but when it swings in close to its companion, the immense gravitational forces or the intense stellar wind from the neighbor could trigger eruptions on the magnetar's surface, causing those powerful bursts. It's a celestial dance, with the bursts as the periodic flash of the dancer's skirt. This wasn't random chaos, it was a structured, predictable pattern hidden within the most energetic phenomena in the universe, suggesting that even these violent events can be governed by the orderly laws of orbital mechanics. While FRB 1809-16 gave us the gift of predictability, its contemporary FRB 1905-20 offered something entirely different and just as valuable, a constant companion. Discovered by the 500-meter aperture spherical radio telescope in China, this repeater, located 3 billion light-years away, came with an extra surprise. Alongside its brilliant milliseconds-long flashes, astronomers detected a faint, persistent radio source emanating from the exact same spot. This was unprecedented. It was as if you had a camera that only caught the flash of a lighthouse beam, and then one day you realized the entire lighthouse structure itself was also glowing dimly but steadily all the time. This persistent radio hum changes everything. It means the environment around this FRB is not quieting down between bursts, something is constantly energizing it. One compelling explanation is that the FRB source is a very young magnetar, perhaps only decades or centuries old, still embedded within the expanding nebula of debris from the supernova that created it. This nebula, a cloud of hot, magnetized particles, would glow steadily in radio waves. The magnetar at its heart would then periodically unleash its colossal bursts, like a toddler having tantrums while sitting in its own messy, energetic crib. This scenario paints a picture of a dynamic, evolving system, a celestial object in its fiery youth, and it helps explain why some FRBs repeat and others do not. Perhaps the repeaters are the young, active ones, while the one-off bursts are from older, more isolated magnetars that have cleared their surroundings. Together, these two signals represent a huge leap forward. FRB 1809-16, with its clockwork rhythm, shows us that these events can be part of a binary system governed by orbital periods. FRB 1905-20, with its persistent radio glow, reveals that the local environment around the burst source is often just as important as the source itself. They demonstrate that FRBs are not a single, monolithic phenomenon, but a family of events with different triggers and different habitats. We are moving from simply detecting these strange flashes to truly understanding the intricate physics and the dramatic cosmic neighborhoods that give birth to them. Our journey now brings us closer to home, to the very stars we see with the naked eye and the confounding signals that remind us the greatest challenge isn't just hearing the cosmos, but interpreting its message correctly. We begin with a signal not from the void, but from the heart of one of the universe's most extreme objects. In 2022, astronomers monitoring a neutron star, a pulsar some 1,300 light-years away, witnessed something bizarre. Without warning, this cosmic metronome, known for its perfectly timed pulses for decades, suddenly started spinning faster. For a fraction of a second, its rotation rate jumped, a sudden increase in frequency scientists call a glitch. Then, just as abruptly, it began to slow down again, but not back to its original rhythm. It settled into a new, slightly faster tempo, as if the universe itself had hit a bump on the road and the instrument needed a moment to recalibrate. While glitches themselves are not entirely unheard of in pulsars, the specific two-stage process of this event was highly unusual. The leading theory is a dramatic one, a starquake. Imagine this neutron star, a sphere of ultra-dense matter so compressed that a teaspoon of it would weigh 1 billion tons on Earth. Its crust, a rigid lattice of atomic nuclei, is under unimaginable strain from the insane rotational forces and a superfluid core spinning within it. Scientists believe this crust can suddenly crack like the tectonic plates on our own planet, but on a scale of cosmic violence. This stellar earthquake would cause the star's rigid outer shell to suddenly shrink ever so slightly, making it spin faster due to the conservation of angular momentum, much like an ice skater pulling their arms in. The subsequent slowdown and reset could be the superfluid core, which had been spinning independently, suddenly coupling back with the crust and transferring energy. This event, dubbed the glitch, was a stunning reminder that even these seemingly dead clockwork objects are dynamic and still full of surprises, offering us a rare laboratory to study the behavior of matter under conditions we can never hope to recreate on Earth. Yet for all its violence, this signal's origin was never in doubt. It was a natural, if spectacular, astrophysical event. The same cannot be said for our next two signals, which emerged from the star system closest to our own and plunged the search for extraterrestrial intelligence into a modern-day roller coaster of excitement and rigorous skepticism. In April and May of 2019, the Parkes Radio Telescope in Australia was observing Proxima-Centauri, a red dwarf just 4.2 light-years away, as part of the Breakthrough Listen project. This star is known to host at least 2 planets, one of which, Proxima-Centauri-b, orbits within the habitable zone where liquid water could exist. The project's algorithms, sifting through the data months later, flagged something extraordinary, a narrowband radio signal at 982 MHz that appeared to be coming directly from the direction of the star. This was not a wide, splattering burst. It was a pure, focused tone, the kind of signal our own technology produces. Even more intriguingly, it subtly drifted in frequency, exactly as you would expect if it were coming from a planet orbiting the star, subject to the Doppler shift. The candidate was named BLC-1 Breakthrough Listen Candidate 1. The discovery was electrifying. It was, on paper, the most compelling candidate signal since WOW. It came from the nearest star system, one we know has a rocky planet in the right place for life. The signal itself seemed to lack any modulation that would carry information, which for some theorists made it even more believable as a simple, purposeful hailing signal meant to be easily noticed. The team, having learned from past episodes, was immediately and publicly cautious. They did not announce a discovery, they announced a mystery that required solving. This kicked off a year-long, painstaking investigation, a masterclass in modern scientific detective work. The first clue was that the signal was only ever detected by Parkes, and only during 5 separate observations over 2 days. Other telescopes pointed at Proxima-Centauri heard nothing. This was strange for an alien broadcast powerful enough to cross interstellar space. The investigation then turned to the signal's properties. While it did drift, the drift was not a smooth curve as would be caused by a planet's orbit. It was a collection of discrete tones that together created the illusion of a drift. The final, definitive blow came from a simple but brilliant test. The researchers considered every single piece of electronic equipment operating in the vicinity of the Parkes telescope. They began systematically turning them off and on while observing. They found the culprit, a cheap, battery-powered oscillator in a piece of equipment that had been installed years prior. When they powered this device on, it emitted a harmonic frequency that was a perfect match for the BLC-1 signal. It was human-made radio frequency interference, plain and simple. The subtle drift was caused by small changes in the temperature of the electronic component, which slightly altered its frequency over time. BLC-1 was not a message from our nearest stellar neighbor. It was a whisper from a faulty circuit board in the telescope's own backyard, a haunting lesson in how our own technological clutter is the greatest obstacle to finding a signal from beyond. But the story of Proxima Centauri doesn't end there. Even as BLC-1 was being debunked, another signal from the same star was making waves. This one, detected at 5 GHz by other instruments, was also a narrowband candidate. However, this new signal was almost immediately identified as the harmonic frequency of a known, active Earth-orbiting satellite. Its appearance near Proxima Centauri was a simple coincidence of the telescope's pointing direction. These two Proxima signals, BLC-1 and its successor, form a perfect diptych of the modern SETI struggle. They represent the immense promise of our increasingly sophisticated technology and listening campaigns, capable of finding needles in the cosmic haystack. But they also underscore the brutal reality that we have filled our own atmosphere with an ever-growing cacophony of artificial signals, creating false alarms that are increasingly difficult to distinguish from the real thing. The search continues, not with disappointment, but with sharper tools and a wiser, more disciplined approach, forever listening for a signal that can pass every test we throw at it. And so our search for cosmic truth leads us to a tale not of deep space, but of a humble kitchen appliance, and a mystery that perfectly illustrates one of the greatest challenges in modern astronomy, knowing what to ignore. For nearly a decade, starting in 1998, astronomers at the Parkes Radio Telescope in Australia were detecting something bizarre. They were seeing strange, dispersed radio bursts that looked, for all intents and purposes, like they were coming from deep space. They named these signals Puritans, after a mythical winged stag that casts the shadow of a man, a creature that is not what it appears to be, and the name was prophetic because these signals were the ultimate cosmic imposters. The Puritans shared a crucial characteristic with the newly discovered fast radio bursts. They showed that telltale signature of dispersion, the smearing of frequencies that indicates a signal has traveled through vast amounts of interstellar plasma. They seemed to be the real deal, but there were clues that something was amiss. Unlike true FRBs, which appear to come from a single point in the distant cosmos, perytons were always detected by the telescope's 13 beams simultaneously. This meant the source was incredibly close, flooding the entire dish with radio noise. They also only ever appeared during daytime working hours at the observatory, which was a huge red flag. Cosmic signals don't care what time it is in Australia. The hunt for the source became a long-running detective story that pitted the astronomers against a phantom in their own backyard. They investigated every possible culprit. They considered aircraft passing overhead, the observatory's own generators, and even local wind turbines. They installed a radio monitor at the telescope site to catch any interference, but the perytons remained elusive, continuing to pop up randomly and muddying the waters in the urgent search for genuine FRBs. For years, this terrestrial ghost haunted one of the world's premier radio observatories, casting a shadow of doubt over every strange signal they detected. How could they be sure a new burst was from a distant galaxy and not another one of these frustratingly local perytons? The mystery was finally cracked in 2015, not by a complex radio filter, but by a simple, brilliant piece of deduction. An astronomer at the site, Emily Petrov, noticed a crucial pattern. The signals were not just happening during the day, they were clustered around lunchtime. The suspicion turned to the staff microwave oven in the observatory's kitchen. They set up an experiment. They placed a radio receiver near the microwave, and then, crucially, they began opening the oven door before the timer had finished. And there it was. The act of interrupting the microwave's operation caused it to emit a brief, powerful burst of radio waves at exactly the frequency of the perytons. The dispersion signature, it turned out, was an illusion created by the telescope's own signal processing when it was hit by such an intense, instantaneous blast of radio frequency interference. The mythical cosmic stag was in fact an astronomer reheating their lunch and being a little too impatient to wait for the beep. The resolution was hilarious, but its lesson was profound. The peryton saga is a cornerstone story in modern science. It highlights the immense difficulty of searching for a needle in a cosmic haystack when we are constantly throwing our own needles into the air. It forced radio astronomers to develop far more rigorous methods for identifying and filtering out terrestrial interference, making the entire field of FRB research more robust and credible. The perytons were a decade-long nuisance, but they were a necessary nuisance. They taught a generation of scientists a masterclass in humility and skepticism, proving that the most important step in finding a signal from beyond is first learning to recognize all the ways we can fool ourselves. Just when we thought cosmic signals couldn't get any stranger, the universe delivered a Christmas present that left astronomers utterly bewildered. On December 25, 2010, the Swift Gamma-ray satellite was quietly orbiting Earth when its sensors were suddenly flooded with an intense burst of high-energy radiation. This was no ordinary event. It was a gamma-ray burst, one of the most violent explosions in the universe, but this one was peculiar from the very start. Dubbed the Christmas burst, or officially GRB 101225A, it didn't behave like any GRB observed before. Instead of fading quickly, it lingered, glowing brightly for an astonishingly long time, its afterglow persisting for days in a beautiful, mysterious display that defied all conventional explanations. Typically, gamma-ray bursts fall into two categories. There are the short bursts lasting less than 2 seconds, believed to be caused by the merger of two ultra-dense neutron stars. Then there are the long bursts which can go on for minutes and are the death cries of massive stars as they collapse into black holes, triggering a supernova. The Christmas burst, however, fit neatly into neither box. Its initial gamma-ray emission lasted a curious 28 minutes, placing it firmly in the long category. But when astronomers rushed to train their optical and radio telescopes on the location, expecting to see the signature of a supernova, they found nothing. No star had died in that region. The afterglow itself was bizarre, fading in a way that didn't match the clean, predictable curve of a stellar explosion. It was a cosmic outlier, a brilliant puzzle wrapped in festive mystery. With the standard models failing, theorists had to get creative. One of the most fascinating and delightfully bizarre hypotheses proposed that we were witnessing a cosmic collision of epic proportions, but on a very small scale. The suggestion was that a comet-like object, a massive body composed of rock and ice, had been pulled into a fatal orbit around a neutron star. Imagine this city-sized stellar remnant, 1 billion times more massive than a mountain, with a gravitational field so intense it could shred anything that came near it. As this poor comet spiraled inward, it would have been torn apart by immense tidal forces, its material smearing into a glowing, hot disk around the neutron star before finally crashing onto its surface. The incredible energy released from the impact and subsequent accretion would have generated that long, strange gamma-ray flash and its persistent afterglow. It was a theory that transformed the event from a stellar catastrophe into a celestial demolition, a violent act of cosmic consumption. Yet another compelling theory argued that we were seeing a supernova after all, just a very unusual one. This model proposed that the explosion was not from a lone massive star, but from a binary system where a neutron star was orbiting a helium-rich giant star. When the giant star finally went supernova, the blast would have engulfed its dense companion. The neutron star, acting like a cosmic plow, would have churned through the expanding shell of debris, injecting enormous energy into it and creating the unusually long-lasting and bright afterglow that so confused observers. This scenario painted a picture of a stellar partnership ending in a spectacularly violent embrace. The true nature of the Christmas burst remains an open debate, a testament to the fact that even within well-studied classes of cosmic events, the universe always has room for surprises. It may have been a comet meeting a gruesome end, a supernova with a twist, or perhaps something entirely different that we haven't even considered yet. This single event showcases the incredible diversity of signals the cosmos can produce. It reminds us that for every rule we establish, there is an exception waiting in the depths of space, a beautiful anomaly that challenges our models and pushes our understanding forward, proving that the universe is always more imaginative than we are. Yet, just as we unravel the mysteries within our cosmic neighborhood, we encounter a phenomenon that challenges the very foundation of modern cosmology, a discovery that suggests the entire observable universe might be caught in a current flowing toward something we cannot see. This brings us to one of the most profound and controversial anomalies ever detected, a signal not in radio waves or light, but etched into the faint afterglow of the Big Bang itself. It's known as the dark flow. To understand this mystery, we must first revisit the cosmic microwave background, or CMB. This is the oldest light in the universe, a cold, faint whisper of radiation that fills all of space, a remnant from when the cosmos was just 380,000 years old. According to our fundamental cosmological principle, the universe should be isotropic on the largest scales, meaning it should look roughly the same in every direction. The CMB is the ultimate proof of this. It is incredibly uniform, with temperature variations of only about 1 part in 100,000. This uniformity is the bedrock of our understanding. But what if this bedrock had a subtle, hidden tilt? That's exactly what a team of astronomers, led by Alexander Kashlinsky, believed they had found. They weren't looking at the temperature of the CMB itself, but at something far more subtle: its kinetic effect on huge clusters of galaxies. The idea is brilliant in its simplicity. As the CMB photons travel across the universe, they can interact with the hot gas that permeates massive galaxy clusters. If those clusters are moving relative to the overall expansion of the universe, the photons get a slight energy boost. This is known as the kinematic Sunyaev-Zeldovich effect. It's incredibly faint, but by carefully studying this subtle distortion in the CMB around hundreds of clusters, the team could effectively map their motion. What they found was staggering. The data revealed that these enormous clusters, each containing the mass of thousands of galaxies, were not moving randomly. Instead, they appeared to be streaming together in a coherent, bulk flow at velocities of over 600 miles per second toward a specific region of space between the constellations of Centaurus and Vela. This wasn't just a few clusters. The flow seemed to extend across billions of light years, a coordinated motion on a scale so vast it defies belief. The most startling implication is that this motion appears to be caused by the gravitational pull of something immense that lies far, far beyond the edge of our observable universe. The very idea sends ripples through the field of cosmology. By definition, we cannot see anything beyond the cosmic horizon, the limit from which light has had time to reach us since the Big Bang. Nothing within the observable universe should be able to exert such a coordinated pull on so much matter. The proposed explanation, therefore, is as mind-bending as the observation itself. It suggests that the structure of the universe extends far beyond what we can see, and that the inflationary period that created our cosmos may have been uneven, seeding regions of vastly different density. The dark flow could be the gravitational signature of a massive superstructure, another universe, or a region of space with a density so extreme it warps the fabric of our own cosmos, tugging on us from the other side of the veil. Naturally, a claim this extraordinary faces intense scrutiny. Critics have suggested that the signal could be an artifact of the method itself, perhaps an incomplete model of our own solar system's motion, or an unaccounted for systematic error in the delicate measurements. Some analyses using different datasets have failed to confirm the effect, yet Kashlinsky and other teams have continued to find evidence for it, refining their methods and using newer, more precise data from telescopes like Planck. The debate is far from settled, but the mere possibility of the dark flow forces us to confront the limits of our knowledge. It hints that our universe is not an isolated island, but might be part of a much larger and utterly mysterious multiverse, whose invisible contours are gently guiding the motion of galaxies on the grandest scale imaginable. It is a ghostly current in the cosmic ocean, and we are only just beginning to sense its pull. But if the dark flow hints at a pull from beyond our horizon, the next signal on our list points to something even more fundamental, a potential fingerprint left on the universe at the moment of its birth, a cosmic alignment that seems to defy one of our most sacred principles. We're talking about the so-called axis of evil, a name that perfectly captures both the startling nature of this anomaly and the profound unease it has caused within cosmology. To understand it, we once again return to the cosmic microwave background, that pristine snapshot of the infant universe. The standard model of cosmology, the lambda cold dark matter model, rests upon a foundational pillar known as the cosmological principle. This principle states that on the largest scales, the universe is homogeneous and isotropic. It should look the same in all directions, with no preferred center, no special axis, and no grand structure that breaks this perfect symmetry. The CMB is the ultimate test of this principle, and for the most part it passes with flying colors, its temperature variations appearing random and evenly distributed. But when scientists looked closer, they began to see a pattern that should not exist. The anomaly was first noticed in data from NAS, a Wilkinson Microwave Anisotropy Probe, or WMAP, and was later confirmed with even greater precision by the European Space Agency's Planck satellite. When researchers mapped the largest scale fluctuations in the CMB's temperature, they didn't find perfect randomness. Instead, they found that these fluctuations appeared to be subtly aligned along a particular axis that runs through our solar system. This alignment, this preferred direction in the cosmos, is what was dramatically dubbed the axis of evil. It's as if the universe has a north and south pole, a concept that directly challenges the isotropic nature demanded by the cosmological principle. The chance of this alignment happening randomly is incredibly small, less than 1 in 1,000. suggesting that either we are seeing a statistical fluke of monumental proportions or our fundamental understanding of the universe's beginnings is incomplete. This discovery has sent theorists scrambling for explanations, and the possibilities are as thrilling as they are diverse. One line of thinking suggests that this alignment could be a relic from the earliest moments of the universe, a fossil imprint from the era of inflation. Perhaps the quantum fluctuations that were stretched across the cosmos to seed all future structure were not perfectly random but had a slight preferential direction baked into them from the very first fractions of a second. Another, even more mind-bending idea proposes that this axis could be a sign of something that existed before the Big Bang. If our universe was born from the collision of two higher-dimensional brains in a multiverse, or if it inherits properties from a prior cosmological phase, that pre-existing physics could have imposed a directionality on our entire cosmos, a kind of cosmic grain that we can still detect today. Yet, for all these exciting theories, the axis of evil remains a deeply contentious topic. A significant number of scientists argue compellingly that this is not a flaw in the universe but a flaw in our perception. The most persistent criticism is that we are seeing a case of cosmic foreground contamination. Our view of the pristine CMB is filtered through the messy foreground of our own Milky Way galaxy. Dust, gas, and synchrotron radiation from our galactic neighborhood could be creating a pattern that mimics a large-scale alignment, fooling our instruments and our analysis. Other skeptics point to subtle biases in the data processing methods themselves, suggesting that the way we clean the raw satellite data to isolate the CMB signal might inadvertently be creating or amplifying this apparent axis. After all, when you're measuring variations of 1 part in 100,000, even the tiniest unaccounted for error can create a signal that looks profound. The debate rages on because the stakes are so high. Confirming the axis of evil as a real feature of the cosmos would necessitate a radical rewrite of our most successful cosmological model, forcing us to accept that the universe has a preferred direction and is not the same everywhere. For now, it stands as one of cosmology's greatest unsolved puzzles, a mysterious whisper of direction in a universe that was supposed to be perfectly random, a ghost in the machine of creation that continues to challenge everything we think we know. While our search has largely focused on the radio and optical realms, some of the universe's most persistent mysteries are written in a different kind of light altogether, infrared. This brings us to a puzzle that has been hiding in plain sight for decades, a set of spectral lines so common they are detected everywhere we look, yet their origin remains one of astrochemistry's most enduring secrets. They are known as the unidentified infrared bands, or UIBs for short. Unlike a single, fleeting burst, these signals are a constant cosmic background hum. Since their discovery in the 1970s, these mysterious infrared emissions have been detected in virtually every corner of the universe we've pointed our telescopes at. They glow within the vast clouds of gas and dust in our own Milky Way. They shine from distant planetary nebulae, and they even emanate from the hearts of other galaxies. What makes them so baffling to scientists isn't their rarity, but their sheer ubiquity and their stubborn refusal to be identified. In the world of spectroscopy, where every molecule has a unique vibrational fingerprint, a specific set of wavelengths at which it absorbs or emits light, these bands are like finding the same set of unfamiliar fingerprints at every single crime scene in the universe. The bands themselves appear as a series of strong, specific emission lines at wavelengths of 3.3, 6.2, 7.7, 8.6, and 11.3 micrometers. For decades, astronomers and chemists have been trying to match these spectral signatures to known molecules in laboratory experiments here on Earth. The hunt has been exhaustive, yet every proposed candidate has fallen short. The pattern doesn't correspond to any simple, common gas like carbon monoxide or water vapor. This failure points to something more complex, something more robust, and something that seems to be a fundamental component of interstellar space. The leading and most fascinating hypothesis is that we are seeing the infrared glow of a large family of organic molecules known as polycyclic aromatic hydrocarbons, or PAH. Picture these not as a single molecule but as a class of compounds. Their structure is like microscopic flakes of graphite or tiny, multi-ringed honeycombs made entirely of carbon and hydrogen atoms. Think of them as the basic building blocks of soot. When a pH molecule is floating in space and gets struck by a single ultraviolet photon from a nearby star, it begins to vibrate intensely like a tuning fork struck with a mallet. It then releases that energy by emitting infrared light at very specific wavelengths that correspond to the stretching and bending of its carbon-carbon and carbon-hydrogen bonds. And remarkably, the predicted emission features of these pH molecules match the unidentified infrared bands almost perfectly. This potential solution is incredibly compelling because it suggests that complex organic molecules, the very kind that form the basis of life on Earth, are not rare at all. They are everywhere, literally filling the space between the stars. They would be a fundamental ingredient in the recipe of the cosmos, manufactured in the outflows of old stars and spread across galaxies by stellar winds. The idea that we are surrounded by a faint infrared haze of these life-bearing compounds is a profoundly beautiful one. However, the case is not yet closed. While the pH model is the best fit we have, it's not a perfect one. The exact details of the observed spectra have subtle discrepancies that laboratory experiments have struggled to replicate perfectly. The extreme conditions of space, the intense radiation fields, and near vacuum might be causing these molecules to behave in ways we can't yet reproduce on Earth. Some scientists even speculate that the carriers could be something more exotic, like hydrogenated amorphous carbon grains or even nanodiamonds, though these ideas are considered less likely. The true nature of the unidentified infrared bands represents a humbling gap in our knowledge. It's a reminder that even with our powerful telescopes and advanced spectroscopy, we are still learning the basic vocabulary of the universe's chemical language. Solving this puzzle is about more than just putting a name to some spectral lines. It's about understanding the distribution of the raw materials for life itself across the cosmos. These mysterious bands are a silent, glowing testament to the fact that the universe is not only stranger than we imagine, but that it is also far more organic and chemically rich than we have yet been able to prove. And yet, for all these tantalizing hints and mysterious signals, the cosmos presents us with a far more profound and unsettling enigma, one that stands in stark contrast to the hopeful crackle of the radio spectrum. It is the sound of nothing, the crushing, overwhelming, and deeply puzzling silence that greets our most earnest attempts to listen. This is the heart of the Fermi paradox, a question so simple a child could ask it, yet so profound that it has haunted scientists and philosophers for generations. If the universe is so vast and so old, and if life is even remotely possible, then where is everybody? The numbers themselves are a compelling argument for cosmic company. Consider our own Milky Way galaxy alone. It contains an estimated 100 to 400 billion stars. A significant portion of those are stable, long-lived sun-like stars. Current data from planet-hunting missions like Kepler suggests that nearly every one of these stars hosts at least one planet, with a staggering number of those worlds orbiting within their star's habitable zone, that Goldilocks region where temperatures could allow for liquid water. With such incomprehensible numbers, the statistical probability that Earth is the only planet to have spawned life seems vanishingly small. The universe should be teeming, a vibrant galactic community buzzing with activity. And yet, when we train our most sensitive instruments on the heavens, we are met with what the Italian physicist Enrico Fermi so succinctly summarized as the Great Silence. This paradox forces us to confront a series of deeply unsettling possibilities, often called the Great Filters. The idea is that there exists some kind of barrier, a nearly insurmountable challenge that prevents life from progressing to the point of becoming a visible, spacefaring civilization. The terrifying question is not whether the filter exists, but where it lies on the timeline of development. Is it behind us? Perhaps the emergence of simple life is actually extraordinarily rare, a chemical fluke that happened here but almost nowhere else. Or maybe the jump from simple prokaryotic cells to complex eukaryotic life was the true miracle, a bottleneck that took billions of years to overcome on Earth and might be nearly impossible elsewhere. If the filter is in our past, it means we are unfathomably lucky, but we are also likely alone, the sole conscious witnesses to a silent universe. The more horrifying alternative is that the great filter lies ahead of us. This is the solution that keeps astronomers awake at night. It suggests that the development of advanced technology and a global civilization inevitably leads to self-destruction. Perhaps every intelligent species that reaches our level of technological maturity soon creates its own doom, through nuclear annihilation, runaway climate change, engineered pandemics, or a malevolent artificial intelligence. In this grim scenario, the silence we hear is not a sign of our solitude, but a galactic graveyard, a universe littered with the ruins of civilizations that bloomed brightly and then snuffed themselves out before they could learn to shout across the stars. Other solutions are less apocalyptic but no less profound. One of the most intriguing is the zoo hypothesis. This idea suggests that we are not alone, but we are being deliberately quarantined or observed. A vastly older and more advanced galactic civilization might be aware of our presence, but has chosen to place us in a kind of cosmic wildlife preserve, allowing us to develop naturally and without interference until we reach a certain level of maturity or wisdom. Our planet might be off-limits, a protected exhibit in a grand interstellar conservation effort. The silence, then, is not an absence but a policy. We are being left alone, and the moment we truly prove we are ready to join the galactic community might be the moment the silence finally breaks. Another possibility is that we are simply looking for the wrong things or in the wrong way. Our search, largely focused on radio waves, might be akin to waiting for a smoke signal in the age of the fiber optic cable. A civilization just a few centuries more advanced than us might have moved entirely beyond such primitive, wasteful forms of communication. They could be using neutrino beams, quantum entanglement, or some other physics we haven't even discovered yet to communicate across the vast interstellar distances. Their conversations could be flowing all around us, a hidden layer of reality we are not yet technologically equipped to perceive. The universe might not be silent, we might just be deaf to its true language. Or perhaps the answer is even more humbling. The distances between stars are so immense and the timescales of cosmic evolution so vast that civilizations simply never overlap. One might rise, flourish for 100,000 years, a mere blink in galactic time, and then vanish, leaving behind only ruins that are eventually erased by the slow churn of cosmic evolution. The chances of two civilizations existing close enough in both space and time to detect each other might be astronomically small. We could be like ships passing in an infinite, dark ocean, separated not just by leagues of water but by millennia of time. The Great Silence, therefore, is not a puzzle to be solved, but the natural, lonely state of the universe. It is the sound of isolation on a cosmic scale, a reminder of the sheer physical difficulty of connection across the gulf of space and time. This silence is the ultimate signal, and its message is one of profound perspective, reminding us of both our incredible rarity and our immense responsibility as the only voice we know of, for now, in the immense and quiet dark. Just as we contemplate the universe's profound silence, a visitor arrived to remind us that some mysteries are not distant whispers, but tangible objects passing right through our celestial neighborhood. In October 2017, the Pan-STARRS telescope in Hawaii detected a faint, fast-moving point of light that immediately stood out from the countless stars and asteroids it tracked each night. Its trajectory was hyperbolic, meaning it was not bound by the sun's gravity. This was no ordinary space rock. It was the first confirmed interstellar object ever observed passing through our solar system. They named it Oumuamua, a Hawaiian word meaning scout or messenger from afar arriving first, and it brought with it a series of puzzles that would ignite one of the most spirited debates in modern astronomy. From the very beginning, Oumuamua defied easy classification. As telescopes around the world swiveled to observe it during its brief flyby, they were met with a series of surprises. The first was its strange light curve. As it tumbled through space, its brightness varied dramatically by a factor of 10. This extreme fluctuation suggested an object with a highly unusual shape. The best fit for the data was an elongated, cigar-like form, perhaps 5 to 10 times longer than it was wide, a shape unlike any asteroid or comet seen in our own solar system. Then came the true head-scratcher, its acceleration. As Oumuamua sped away from the sun, astronomers carefully tracked its path. They found it was not following a purely gravitational trajectory. Something was giving it an extra push, a tiny but measurable non-gravitational acceleration that could not be explained by the sun's pull alone. For comets, this is a common occurrence. As they approach the sun, their icy surfaces heat up, releasing gas and dust that jet out into space, acting like a natural thruster. This outgassing creates a visible coma, a fuzzy atmosphere, and often spectacular tails. But Oumuamua showed no such thing. Despite intense scrutiny by some of the world's most powerful telescopes, including the Hubble Space Telescope, no coma, no dust, no gas, no tail of any kind was ever detected. It was a completely dry, inert object, yet it was accelerating as if it had a hidden engine. This was the central contradiction that launched 1,000 theories. The scientific community scrambled for natural explanations. One of the most prominent ideas proposed that Oumuamua was a hydrogen iceberg. The theory suggested that in the cold, dense cores of giant molecular clouds, where temperatures are just a few degrees above absolute zero, large chunks of solid hydrogen could form. As such an object neared the sun, the theory went, the solar radiation would heat it, causing solid hydrogen to sublimate directly into gas, providing the thrust for the acceleration without producing any visible dust or complex gases that our instruments could easily detect. While elegant, many physicists found this idea problematic. A pure hydrogen iceberg would be incredibly fragile, likely evaporating long before it could travel the immense distances between stars, let alone survive a close pass by the sun. Other natural explanations included the idea that it was a chunk of nitrogen ice, similar to what is found on the surface of Pluto. When heated by the sun, the nitrogen would sublimate, again providing the necessary thrust without a visible tail. Yet, to get the observed acceleration, Oumuamua would have had to be composed of a tremendous amount of nitrogen ice, which raised questions about how such a large, pure fragment could be ejected from a planetary system. Another camp argued it was a dust bunny, a highly porous, fractal-like aggregate of dust grains with such low density that radiation pressure from the sun itself could have provided the push. Each natural model had its merits, but each also struggled to perfectly explain the complete set of Oumuamua's oddities without invoking some new, never-before-seen type of celestial object. It was this very struggle that led Harvard astronomer Avi Loeb to propose a more extraordinary hypothesis. If all the natural explanations required inventing a new class of object that we had never seen, he argued, then we must also consider artificial origins. Perhaps Oumuamua was not a rock but a piece of advanced technology. The specific shape of the acceleration, he noted, was precisely what you would expect from a light sail. A light sail is a speculative form of propulsion that uses the gentle pressure of sunlight for thrust, much like a boat's sail uses wind. A thin, lightweight object of the proposed size and shape could indeed be pushed by sunlight in a way that perfectly matches the anomalous acceleration observed. Loeb suggested Oumuamua could be a discarded light sail from an interstellar vessel, a piece of floating debris from another civilization, or even a purposeful probe sent to reconnoiter our star system. This idea, while captivating to the public, was met with intense skepticism from much of the astronomical community. Critics pointed out that Occam's razor, the principle that the simplest solution is often the correct one, still favored a natural origin, even an unusual one. They argued that invoking aliens should always be the last resort, not the first. The debate quickly spilled out of scientific journals and into the global media, becoming a classic clash between cautious, conservative scientific interpretation and bold, speculative theorizing. It was a healthy, if sometimes heated, scientific discourse, highlighting how the same data can be interpreted in wildly different ways when confronting a truly novel phenomenon. The ultimate frustration, and the core reason the debate remains unresolved, is that Oumuamua is now gone. It is already far beyond the orbit of Neptune, speeding out of our solar system into the blackness of interstellar space, far too faint for any current telescope to observe further. We captured only a few weeks of data on this mysterious visitor, a fleeting glimpse that provided more questions than answers. Its legacy, however, is immense. It proved that interstellar objects are common enough that one passed right by us, and it has spurred astronomers to prepare for the next one, new projects like the Vera C. Rubin Observatory are designed to detect these visitors much earlier, allowing us to study them in far greater detail. Oumuamua was a cosmic scout, a messenger that told us we live in a galaxy that regularly exchanges material between stars. Its enduring mystery is a powerful reminder that sometimes the most profound discoveries are not just about finding answers, but about learning just how many new and wonderful questions the universe still has to ask. While the hunt for dark matter often involves massive detectors buried deep underground, a new and elegant approach is tuning into the cosmos itself, listening for the faintest of radio whispers that could finally reveal the universe's most elusive component. This brings us to a frontier known as action radio-astronomy, a field that transforms the entire universe into a vast natural laboratory. The core idea rests on a leading candidate for dark matter, the action. This hypothetical particle was originally proposed not to explain the missing mass of the universe, but to solve a deep and esoteric problem in particle physics known as the strong CP problem. Yet, in a beautiful twist, its properties also make it a perfect candidate for the cold dark matter that shapes the cosmos. Actions are thought to be incredibly light, nearly massless, and they would flood the universe in staggering numbers, forming a cold, invisible ocean through which galaxies and stars move. But unlike the particles we know, actions don't interact via the electromagnetic force. They don't absorb or emit light, which is precisely why they've remained dark. However, under the right conditions, theory predicts they can undergo a miraculous transformation. This is where the radio part comes in the presence of an immensely powerful magnetic field, like those found around neutron stars within galaxy clusters, or even generated by our own magnets in laboratories, an action can convert into a photon. It's a kind of particle alchemy where a dark matter particle spontaneously becomes a particle of light. The frequency or energy of that photon is directly tied to the action's mass. For the action masses most theorists are interested in, the resulting photon would fall smack in the middle of the radio wave part of the spectrum. This means that a portion of the unexplained radio static we hear from across the galaxy could in fact be the long-sought voice of dark matter itself, singing its tune on a frequency we're only just learning to decode. Experiments like the Action Dark Matter Experiment, or ADMX, have been pioneering this search in controlled lab settings, using powerful superconducting magnets and incredibly sensitive radio receivers to listen for the faint photon ping of an action conversion. But the real cosmic potential lies in looking outward. Astronomers are now using entire celestial objects as their experimental apparatus. They point radio telescopes toward regions of space that are naturally filled with strong magnetic fields, but are otherwise seemingly empty of conventional radio sources. A prime target is the halo of our own Milky Way galaxy. If the galactic halo is indeed saturated with a cloud of actions, as theories suggest, then its interaction with the galaxy's own magnetic fields should produce a faint, diffuse radio glow with a very specific signature. The challenge is that this signal would be buried under a cacophony of other radio emissions from cosmic rays, interstellar gas, and distant galaxies. Disentangling the potential action signal from this foreground noise is a Herculean task of data analysis, requiring exquisitely precise models of everything else that emits radio waves. Some of the most tantalizing hints have come from studying not empty space, but the most magnetic objects in the universe, neutron stars. These ultra-dense stellar corpses possess magnetic fields billions of times stronger than Earth. They are essentially nature's pre-built action-to-photon conversion factories. If actions exist in the dark matter halo surrounding a neutron star, the theory predicts that the star's incredible magnetic field would efficiently convert them into radio waves. Crucially, this would produce a very distinctive signal, a narrow, beam-like radio emission that doesn't align with the star's rotational poles like a normal pulsar beam, but instead points in a different direction dictated by the surrounding dark matter. In 2020, a study of a nearby neutron star known as the Magnificent Seven reported an unexplained excess radio signal that matched these predictions. The excitement was palpable as it seemed to fit the profile of an action-generated broadcast. However, subsequent observations and analyses have cast doubt, suggesting the signal might be more mundane, perhaps a previously unknown type of pulsar emission. This is the frustrating yet essential cycle of scientific discovery. A thrilling candidate emerges only to be subjected to intense scrutiny that more often than not reveals a conventional explanation. Despite these setbacks, the search is accelerating, driven by the profound implications of a detection. Hearing the radio signature of an action would be a monumental Triple Crown achievement for physics. It would simultaneously identify the nature of dark matter, validate a solution to a decades-old problem in quantum theory, and potentially open a window into entirely new realms of particle physics. Unexplained radio signals from galaxy clusters or the quiet depths of interstellar space continue to offer promising targets for this hunt. Each strange, unidentified hum or narrowband whisper detected by our telescopes is now scrutinized through this new lens. Could it be dark matter? The method represents a beautiful synergy between the largest scales of cosmology and the smallest scales of particle physics, using the universe itself as the ultimate instrument to tune into a frequency we have never heard before, one that may hold the key to understanding the true, hidden structure of reality. But if our search for dark matter takes us to the quiet edges of the radio spectrum, our next destination is a place of unimaginable violence and energy, the very heart of our own galaxy, where the signals are anything but faint. Lying 26,000 light-years away, hidden behind thick clouds of cosmic dust, sits the center of the Milky Way. It is a region ruled by a supermassive black hole named Sagittarius, a star, a gravitational titan around which our entire galaxy slowly turns. And surrounding this monster is a menagerie of the most bizarre objects and the most intense, unexplained emissions in the entire galaxy. A collection of mysteries so profound they have been collectively dubbed the galactic center anomaly. One of the most stunning features of this region is something that, surprisingly, we only discovered relatively recently. When NASA's Fermi Gamma Ray Space Telescope began mapping the sky, it revealed two enormous, symmetrical bubbles of energy billowing out from the galactic center, extending 25,000 light-years above and below the plane of the Milky Way. These Fermi bubbles are colossal structures, each one large enough to contain our entire solar system many times over, and they are pouring out immense amounts of high-energy gamma radiation. It's as if our galaxy's core experienced two monstrous, simultaneous eruptions in the distant past, and we are still seeing the magnificent, energetic aftermath. The leading theory suggests that these bubbles are the remnants of a past feeding frenzy by Sagittarius, a star. Perhaps a massive gas cloud or even a small galaxy was torn apart and consumed by the black hole millions of years ago, and in the process, it belched out these gigantic lobes of hot plasma and radiation. However, an alternative and thrilling hypothesis connects these bubbles directly to dark matter. Some physicists propose that the dense concentration of dark matter theorized to exist at the galactic center could be the source. If dark matter particles are their own antimatter counterparts, they might annihilate upon collision, releasing the tremendous bursts of energy that could have inflated these vast structures. The true origin of the Fermi bubbles remains one of the most active debates in astrophysics, a choice between a dramatic historical event and a continuous, invisible particle process happening right in our cosmic backyard. Adding to the peculiarity of this region are the strange inhabitants that orbit perilously close to the black hole itself. Astronomers have discovered a class of objects that defy simple classification, known as G objects. From a distance, they look like compact, innocent clouds of gas, perhaps several astronomical units across. But as they approach their closest point to the black hole on their long, elliptical orbits, they do something extraordinary. They don't get torn apart. A simple cloud of gas would be instantly shredded by the black hole's immense tidal forces, yet the G objects survive their close encounter intact, emerging on the other side of their orbit seemingly unscathed. This incredible resilience suggests they are not just simple clouds. The prevailing theory is that each G object is actually a star, a substantial, massive star, that is hidden at the center of a much larger, distended envelope of gas and dust. Think of it as a stellar matryoshka doll. The central star provides the gravitational glue that holds the entire object together, allowing the outer gas cloud to stretch and distort under the black hole's pull without being completely ripped away. These objects are thought to be the product of stellar mergers, the violent joining of two stars that were once a binary pair, forced together by the relentless gravitational tides of the central black hole. The G objects are a fascinating new class of celestial body, one that can only exist and survive in the most extreme environment our galaxy has to offer. Yet the anomalies do not stop there. The very center of the galaxy is also a hotspot for an overabundance of brilliant young stars, all orbiting in a region where, according to our standard models, they should never have been able to form in the first place. The tidal forces from the black hole are so powerful that they should prevent the giant clouds of gas necessary for star formation from ever collapsing. It would be like trying to build a sandcastle in the middle of a hurricane, and yet there they are. This paradox suggests that the rules of star formation are different in this extreme realm, or that some cataclysmic event, like the collision of two massive gas clouds, compressed material so violently and rapidly that it overcame the black hole's disruptive influence in a single, dramatic burst of creation. Wrapping all of this together is the lingering mystery of the galactic center GVXS. This is a faint, diffuse glow of gamma rays that permeates the central region detected by the Fermi telescope. While some of this emission can be explained by the collective output of pulsars and other high-energy objects, a significant portion remains unaccounted for. Once again, this has led to speculation that we could be seeing the indirect signature of dark matter particle annihilations, a faint but persistent sizzle from the invisible ocean of matter that is believed to be most concentrated there. The galactic center anomaly is not one single mystery, but a layered puzzle of impossible objects, ancient explosions, and unexplained energies. It is a cosmic crime scene, and we are the detectives, piecing together the evidence from the faint signals that have traveled for millennia, trying to understand the violent and magnificent history of the place we call home. While the galactic center presents a symphony of high-energy anomalies, our search for signs of intelligence often brings our focus back to stars much more like our own sun. This brings us to a signal that, for a brief moment in 2015, seemed to promise everything the SETI community had been waiting for. It originated from a star known as HD 164595, located 94 light-years away in the constellation Hercules. On the surface, this star was a perfect candidate. It's a near twin of our own sun, almost identical in size, mass, and luminosity. And astronomers already knew it hosted at least one planet, a Neptune-sized world orbiting very close in, a discovery that naturally sparked the question of whether other, more Earth-like worlds might be hiding in that system. The stage seemed perfectly set for a dramatic discovery. The signal itself was detected by the Ratan 600 radio telescope in Zelenchikskaya, Russia, on May 15, 2015. It was a strong, narrowband signal at a frequency of 11 GHz, a frequency with no known natural process that could produce it. The researchers, led by astronomer Nikolai Bursov of the Russian Academy of Sciences, noted its remarkable strength. They calculated that if the signal had been broadcast in all directions, it would have required an emitter with the energy of a civilization far beyond our own, a so-called Kardashev-type Roman II civilization capable of harnessing the entire power output of its star. However, if it were a highly focused beam, deliberately aimed in our direction, a concept known as an interstellar beacon, the power requirements would drop to a level within the reach of a civilization only slightly more advanced than our own. This tantalizing possibility is what made the signal so immediately compelling. It seemed to fit the profile of a deliberate, targeted transmission. The protocol for such a detection is clear. You do not announce it to the world immediately. You attempt to verify it. The Russian team quietly reached out to their colleagues in the SETI community, and a global effort was quickly mobilized. The Allen Telescope Array in California, along with the Green Bank Telescope in West Virginia, swiftly turned their dishes toward HD 164595, scanning the same frequency with even greater sensitivity. The Breakthrough Listen project also joined the hunt, adding its considerable analytical power to the search. The world held its breath for a few days, waiting to see if the signal would repeat. But the follow-up observations heard only silence. The signal, which had been so strong and clear for that one brief moment at Ratan 600, was gone. It never reappeared. Without that crucial repetition, the signal's credibility evaporated rapidly. The scientific community began a rigorous process of elimination to find a more mundane explanation. The most likely culprit, as it so often is, was terrestrial interference. The 11 GHz frequency is not a protected band. It is used by a wide variety of human technologies, including military radar and satellite communications. The Ratan 600 telescope has a unique design, a large, circular array of reflecting panels. That can sometimes make it particularly susceptible to picking up signals that bounce off aircraft or satellites passing through its field of view. A detailed analysis concluded that the signal's characteristics were almost certainly consistent with a secret Russian military satellite, one whose orbital parameters and transmission frequencies were not public knowledge. The signal's appearance and disappearance aligned perfectly with the passage of such an object through the telescope's beam. It was a classic case of a false positive caused by our own technological clutter. The story of the HD 164595 signal is a crucial chapter in the modern history of SETI, not for what it discovered but for what it demonstrated. It showed how the global scientific community can now react with incredible speed and coordination to investigate a potential candidate. It also highlighted the immense and growing challenge of radio frequency interference, a problem that becomes more difficult every year as we launch more satellites and fill the spectrum with more signals. This event underscored a painful truth. The most convincing evidence for extraterrestrial intelligence will likely not be a single, stunning detection, but a signal that can be detected, verified, and redetected by multiple independent observatories across the world, proving its origin is beyond any shadow of a doubt. It was a reminder that in this grand search, patience and rigorous skepticism are just as important as powerful telescopes and boundless optimism. While we train our most powerful telescopes on distant galaxies and exotic stars, some of the most persistent and personal cosmic mysteries are happening right next door on the surface of our own celestial companion. For centuries, long before the first telescope was even invented, keen-eyed observers have reported strange, fleeting lights on the moon, sudden flashes, ambiguous glows, and areas of dimming that appear and vanish without warning. These are the lunar transient phenomena, or LTP, a catch-all term for a host of brief, mysterious events that transform the face of our seemingly dormant neighbor into a place of subtle, enigmatic activity. The historical record is rich with these accounts. As far back as the year 1178, the English monk Gervase of Canterbury chronicled what he described as a sudden, violent flaming on the upper horn of the new moon, an event so startling it was witnessed by 5 fellow monks. In the 18th century, the renowned astronomer Sir William Herschel, the discoverer of Uranus, observed bright red spots on the lunar surface during a solar eclipse, which he believed so strongly to be volcanic eruptions that he even attempted to inform King George III that the moon was not a dead world. These are not the reports of fringe observers. They come from some of the most respected figures in the history of science, all pointing to a moon that occasionally and unpredictably flickers with light. Modern astronomy has done little to solve the mystery. If anything, it has only deepened it. During the Apollo program, NASA specifically trained its astronauts to watch for these events. In 1969, as Apollo 11 was en route to the moon, Mission Control in Houston asked Neil Armstrong to look toward the crater Aristarchus, which was reportedly glowing with an eerie luminescence. While Armstrong himself didn't see it, countless Earth-based observers have. The catalog of LTP now includes thousands of documented events, ranging from brief, pinpoint flashes that last only a second to large, diffuse reddish glows that can persist for 20 minutes or more, and even instances where certain areas of the lunar surface temporarily darken, as if a patch of gray veil has been drawn across them. So what could possibly be causing these ghostly illuminations on an airless, geologically dead world? Scientists have proposed several compelling natural explanations, each with its own strengths and weaknesses. The leading theory points to outgassing. The idea is that radioactive decay deep within the moon's interior could still be producing small amounts of radon gas. This trapped gas would build up pressure until it eventually finds a weakness in the lunar crust, a fissure or a fault line, and ruptures through to the surface in a sudden, explosive release. As the gas and accompanying dust particles erupt into the vacuum of space, they could scatter sunlight, creating a brief, bright flash or a lingering, hazy cloud that would appear as a glow from Earth. This would be a tiny, localized moonquake of gas, a last, faint whisper of the moon's internal activity. Another strong contender is the constant bombardment of meteoroids. Unlike Earth, the moon has no protective atmosphere to burn up incoming space debris. Even pebble-sized rocks strike the lunar surface with tremendous kinetic energy, instantaneously vaporizing upon impact and creating a short-lived, hot plasma flash visible from Earth. These impact flashes are now regularly documented by astronomers who dedicatedly monitor the dark portion of the moon during meteor showers, providing a firm scientific basis for at least a portion of the observed flashes. However, this theory struggles to explain the longer duration glows, which can last for many minutes, far longer than any impact flash should. Then there are more exotic possibilities. Some scientists have suggested triboluminescence light generated by the grinding and fracturing of subsurface rocks during moonquakes. As tectonic stresses shift the moon's crust, the friction between crystals of quartz or other minerals could produce fleeting sparks of light. Others point to electrostatic phenomena. The moon's surface is constantly bathed in the solar wind, which can give the dusty regolith a strong electric charge. Perhaps under the right conditions, this charge could suddenly discharge, leaping from dust grain to dust grain in a kind of silent, airless lightning storm, creating a localized glow. Despite these plausible theories, a definitive cause for any specific LTP event remains elusive. The fundamental problem is their sheer unpredictability. They are here 1 second and gone the next, offering no opportunity for sustained study. By the time multiple telescopes can be swung toward the coordinates of a reported flash, the event is long over, leaving behind no physical evidence, no warm spot, no new crater, no lingering gas cloud, nothing but a question mark. This evanescent quality has perhaps inevitably fueled more speculative ideas. For a time, some researchers seriously entertained the possibility that we were witnessing evidence of lunar-based intelligent life, a notion that has since been thoroughly dismissed but adds a layer of historical intrigue to the mystery. The true enigma of the lunar transient phenomena is not just their cause but their very location. They challenge our perception of the moon as a static, unchanging museum piece. We sent probes and astronauts there and brought back rocks that spoke of a geologically dead world billions of years old. Yet, these fleeting lights suggest that there may still be small, subtle processes at work deep within its core or on its surface, a low-level geological heartbeat that we have yet to fully understand. They are a reminder that even the most familiar objects in our sky can hold onto their secrets, that wonder doesn't always require a journey to the edge of the observable universe. Sometimes, it's just a glance away, flickering in the tranquil silence of our own night sky. But if the mysteries of the moon remind us that wonder is close at hand, few tales capture the public's imagination quite like the legend of the Black Knight satellite, a story that masterfully blends early space-age history, misunderstood technology, and our deep-seated desire for cosmic companionship. This enduring conspiracy theory tells of an ancient alien spacecraft, tens of thousands of years old, silently orbiting our planet in a polar trajectory, watching and waiting. Its origins, however, are not etched on some ancient astronaut artifact, but in the far more mundane and fascinating history of human spaceflight itself. The story truly begins in 1954, several years before the launch of Sputnik, when newspapers reported that the U.S. Air Force had detected 2 mysterious objects orbiting Earth. The source of this claim was a researcher named Donald Keyhoe, a former Marine Corps naval aviator and a major proponent of the extraterrestrial hypothesis for UFOs. He suggested these objects could be artificial satellites, sparking public speculation about their origin. Then, in 1960, Time magazine reported that the U.S. Navy had tracked a dark, tumbling object in orbit. They gave it a name, the Black Knight. This was during the height of the Cold War, and the immediate, panicked assumption was that it was a secret Soviet spy satellite. The mystery was solved just weeks later when it was identified as the discarded, 8-foot-long payload shroud from a top-secret American spy satellite program called Corona, a case of the U.S. military not being able to recognize its own classified debris. The legend was resurrected years later in 1963 when astronaut Gordon Cooper reported seeing a greenish object ahead of his capsule during his Mercury Atlas 9 mission. Cooper, a steadfast believer in UFOs, reported the sighting to NASA, and tracking stations allegedly picked up the unknown object on radar. For proponents of the Black Knight theory, this was the ultimate smoking gun, an official sighting by a revered American hero. However, the likely explanation was far more human. Cooper's spacecraft was experiencing life-threatening technical failures, including a carbon dioxide buildup, and many historians and fellow astronauts believe the sighting was a hallucination triggered by high levels of CO2, a known physiological effect. NASA official stance was that the object was most likely a panel that had jettisoned from the spacecraft earlier, shimmering in the sunlight. The most iconic piece of evidence, the one that truly cemented the Black Knight in popular culture, emerged from the early days of the Space Shuttle program. In 1998, during the STS-88 mission to construct the International Space Station, astronauts captured a photograph of a strange, angular, black object against the curvature of the Earth. This image, quickly circulated online, was presented as definitive photographic proof of the alien satellite. The truth, as it so often is, was both simpler and more interesting. The object was not an alien craft at all, but a thermal blanket, a piece of protective insulation that had been lost during an earlier spacewalk. The astronauts themselves identified it as such. The image shows a familiar, human-made object adrift in the void, a piece of space junk that briefly took on a mythological life of its own. So how did these disparate events, a misidentified piece of debris, a potential hallucination, and a lost thermal blanket coalesce into a single, persistent legend? The answer lies in a powerful human tendency, pattern recognition. We are hardwired to connect dots, to weave separate threads into a coherent narrative. The name Black Knight itself, with its ominous and Arthurian connotations, provided a perfect vessel for this story. It transformed random, unrelated incidents into chapters of a grand, hidden history, a secret that governments were supposedly covering up. The theory offered a thrilling alternative to the messy, complicated, and often unglamorous reality of space exploration, where the greatest mysteries are often solved by identifying a lost screw or an errant piece of foil. The cultural impact of the Black Knight is in many ways more significant than its astronomical reality. It has appeared in television shows, video games, and countless online forums, becoming a shorthand for the idea that we are not alone and that evidence of this has been in plain sight all along. It represents a fascinating chapter in the history of our relationship with space, a testament to how easily fact and fiction can become entangled in the vacuum above our heads. The Black Knight satellite is not an alien observer, it is a mirror. It reflects our own hopes, our fears, and our boundless capacity for wonder, showing that sometimes the most compelling mysteries are not those whispered by the stars, but those we create for ourselves. Our exploration of the cosmos's great mysteries now takes us to the oldest light there is, the fossilized glow of creation itself, where a single, bizarre anomaly has sparked a debate that stretches to the very edges of reality. This is the story of the cosmic microwave background cold spot, a colossal and profoundly chilly region in the universe's baby picture that simply should not exist. To understand why it's so baffling, we have to revisit the cosmic microwave background, that faint afterglow from when the universe was just 380,000 years old. This radiation is incredibly uniform, a nearly perfect blackbody with tiny, random fluctuations in temperature of about 1 part in 100,000. These tiny ripples are the seeds of all future structure, the galaxies and galaxy clusters we see today. They are the result of quantum fluctuations from the universe's first moments, stretched to cosmic proportions by inflation. For the most part, the map is reassuringly random, but then there's the cold spot, discovered in the data from NASA's Wilkinson microwave anisotropy probe and later confirmed with even greater clarity by the Planck satellite. The cold spot is not a subtle feature. It's a vast circular region in the constellation Eridanus, about 70 angular degrees across. That's an area in the sky over 10 times the diameter of a full moon. Within this enormous patch, the temperature of the CMB is about 70 microkelvins colder than the average surrounding region. That might not sound like much, but on a map defined by minuscule variations, it's a gaping, frigid hole. Statistically, such an extreme deviation is incredibly rare. The odds of it appearing randomly in a universe that follows our standard cosmological models are less than 2%. This isn't just a curiosity, it's a 5 sigma-level problem, a direct challenge to our understanding of the infant universe. Scientists, being natural puzzle solvers, immediately began searching for a conventional explanation. The most straightforward hypothesis was that this wasn't a true feature of the primordial CMB at all, but an effect caused by something lying between us and the cosmic background, a foreground object. The leading candidate was a supervoid. The idea is elegant. If there is a truly enormous region of space between us and the cold spot that is significantly emptier than average, a vast cosmic desert with far fewer galaxies and clusters, then the light from the CMB would have to pass through it. According to the principles of general relativity, as photons travel into a gravitational well, they gain energy, becoming blue-shifted. As they travel out, they lose energy, becoming redshifted. In a static universe, these effects would cancel out, but because our universe is expanding, the well evolves as the photon passes through. The net result is that a photon climbing out of a gravitational well loses more energy than it gained entering it, an effect known as the integrated Sachs-Wolf effect. If the cold spot was caused by a supervoid, the CMB photons would lose a little extra energy traversing this underdense region, making that patch of the sky appear slightly colder. It's a perfect natural explanation. The hunt for this proposed supervoid began. Astronomers mapped the distribution of galaxies in the direction of the cold spot, and indeed, they found evidence of a large underdense region. But here's where the plot thickens. The void they found, while large, doesn't seem to be nearly large enough or empty enough to account for the profound coldness we observe. The energy loss from the integrated Sachs-Wolf effect is relatively small. To create a cold spot of this magnitude, you would need a void of such staggering proportions, perhaps 1 billion light-years across, that it would itself be a major challenge to our models of how structure forms in the universe. We're faced with a dilemma. Either the void is there and is far more extreme than our galaxy surveys can detect, or the void explanation simply doesn't work. This failure of the simplest answer is what opens the door to far more speculative and thrilling possibilities. If the cold isn't caused by something in the way, then it must be a genuine feature imprinted on the CMB at the dawn of time. And this is where the physics gets truly mind-bending. One of the most captivating hypotheses is that the cold spot is a bruise, a cosmic scar left from a collision with another universe. This idea emerges naturally from the theory of eternal inflation and the multiverse. In this model, our universe is just one expanding bubble in a much larger, perhaps infinite, meta-universe. Other bubbles, other universes with different physical constants and laws, are constantly nucleating and expanding. If another universe bubble happened to form very close to ours in the meta-universe and the two expanded into each other, the collision could have left a distinct imprint on the fabric of our cosmos. The energy exchange at the boundary of such a collision could have slightly suppressed the formation of matter and energy in that region, creating a vast underdensity and, crucially, altering the local curvature of space in a way that would make the CMB in that direction appear colder. The cold spot in this breathtaking scenario is the first observational evidence that our universe is not alone. It is one of many in a vast multiverse. Of course, such an extraordinary claim is met with healthy skepticism and alternative theories. Some physicists propose that the cold spot could be the imprint of a cosmic texture. In the very early universe, during a phase transition as fundamental forces separated, topological defects could have formed kinks in the very fabric of spacetime. If one of these defects, known as a texture, collapsed within the first second of the universe, it would have released a tremendous burst of energy that subtly altered the gravitational field in a large region, again creating a cold imprint on the CMB. Others suggest it could be the shadow of a super-large, super-distant cluster of galaxies whose gravitational lensing effect is distorting our view in a way we haven't fully modeled. Each explanation pushes the boundaries of physics and cosmology. The cold spot remains one of the most tantalizing and persistent anomalies in all of science. It is a ghost in the machine of creation, a whisper from the first moments of everything that hints at realities beyond our own. Whether it's ultimately explained by an unseeable void, a shroud of cosmic texture, or a collision with another universe, its existence forces us to question the completeness of our standard model. It is a testament to the fact that even in our most precise map of the ancient cosmos, there are still blank spots, regions of profound mystery that beckon us to look deeper and imagine a reality far grander and more strange than we ever thought possible. Yet, even as we gaze in wonder at these profound puzzles from the past and present, our search is accelerating toward a future brimming with unprecedented technological promise. The next generation of observatories, now in advanced stages of planning and construction, represents a quantum leap in our ability to listen to and observe the cosmos, offering the very real potential to solve enduring mysteries and to uncover new ones we cannot yet even conceive. Leading this charge is a project of almost unimaginable scale and sensitivity, the Square Kilometre Array, or SCAR. This is not a single telescope, but a vast, interconnected network of thousands of dish antennas and up to 1 million low-frequency antennas spread across 2 continents, South Africa and Australia. The name says it all. Its total collecting area will be approximately 1 square kilometre, making it the most sensitive radio telescope ever built by orders of magnitude. The SKA's capabilities are frankly mind-boggling. It will be so sensitive that it could detect an airport radar on a planet orbiting a star tens of light years away. It will survey the sky 10,000 times faster than any current system, mapping the entire visible universe in exquisite detail and tracing the distribution of neutral hydrogen, the basic building block of the universe, further back in time than ever before, to the very dawn of the first stars and galaxies. For the hunt for enigmatic signals, the implications are staggering. The SKA will monitor the entire sky continuously, allowing it to catch fast radio bursts in numbers we can only dream of today, potentially classifying thousands of them and finally revealing their full range of causes. Its precision will allow it to pinpoint their host galaxies with absolute certainty, and its wide frequency range might finally detect the elusive, persistent radio sources predicted to accompany them, confirming whether they are indeed powered by magnetars. And for SETI, the search for extraterrestrial intelligence, the SKA is nothing short of a revolution. It will conduct the most comprehensive and sensitive search for artificial signals ever undertaken, scanning millions of star systems with a fidelity that could finally distinguish between a true cosmic hello and the frustrating radio frequency interference that has plagued previous efforts. While the SKA listens, the James Webb Space Telescope acts as our most powerful eye, peering into the infrared universe with a clarity that has already begun to redefine astrophysics. Unlike Hubble, which primarily sees invisible and ultraviolet light, Webb is designed to detect the heat signatures of the cosmos, allowing it to look through cosmic dust clouds to see the formation of stars and planets, and to gaze back in time to observe the very first galaxies that ignited after the Big Bang. Its contributions to solving signal mysteries are more indirect but equally profound. For an object like Oumuamua, if another interstellar visitor is detected early enough, Webb could analyze its composition by studying the sunlight reflected off its surface, searching for the molecular fingerprints of water ice, organic compounds, or other materials, finally telling us if it was a nitrogen iceberg, a rocky asteroid, or something else entirely. For tabbys-star and other objects exhibiting strange dimming behaviors, Webb's infrared eyes are perfect for studying the detailed structure of the orbiting dust and debris that causes these dimming events, identifying the size and composition of the particles to confirm their origin. And in the hunt for life, Webb is already analyzing the atmospheres of exoplanets, searching for biosignatures like oxygen, methane, and water vapor in worlds orbiting distant stars. It won't see city lights or detect radio broadcasts, but it could find the chemical evidence of a living world, a discovery that would forever change our understanding of our place in the universe and provide the most compelling targets for future SETI campaigns. And those SETI campaigns themselves are entering a new golden age, supercharged by private funding and cutting-edge data analysis. The Breakthrough Listen initiative, funded by billionaire Yuri Milner, is the most comprehensive search for extraterrestrial intelligence in history, dedicating thousands of hours on premier telescopes like the Green Bank Telescope, the Parkes Observatory, and the Automated Planet Finder to scan the nearest million stars, the center of our galaxy, and the entire galactic plane. But its true power lies not just in telescope time, but in its sophisticated data pipeline. Using advanced machine learning and artificial intelligence algorithms, Breakthrough Listen can sift through millions of signals in real time, filtering out terrestrial interference with ever-increasing accuracy and identifying the most promising candidates that exhibit the hallmarks of a truly technological source, like narrowband transmissions or signals with complex modulation. This move from human-sifted data to AI-powered analysis is a game-changer, allowing you to process volumes of information that would be simply impossible for a team of people to handle. The future of this endeavor points toward even more ambitious projects, like plans to use the new Vera-C, Rubin Observatory's legacy survey of space and time to scan the entire night sky for optical laser pulses that could be used as interstellar beacons, a completely different approach to the search. Together, these technological marvels represent a fundamental shift from simply wondering about these cosmic signals to actively and systematically hunting for their solutions. We are moving from an era of accidental discoveries and frustratingly brief glimpses to one of dedicated, holistic observation. The square-kilometer array will hear the universe's whispers with unmatched clarity. The James Webb Space Telescope will see its hidden details with stunning resolution, and Breakthrough Listen will analyze the data with intelligent precision. They form a powerful trifecta of discovery, and it is almost a certainty that they will not only provide answers to the mysteries we've explored today, but will also reveal new phenomena that are, for now, beyond the limits of our imagination. The universe has proven itself to be a place of infinite wonder and surprise, and with these new tools, we are finally building the instruments capable of understanding its deepest and most enigmatic messages. But perhaps the most transformative application of AI lies not in filtering out our own noise, but in identifying signals that a human might never think to look for. We have been searching for narrowband radio signals because that's what our own technology produces. It's a projection of our own capabilities onto the cosmos. But what if an advanced civilization uses a form of communication we haven't even conceived of? This is where AI truly shines, moving from a filter to a discoverer. Machine learning algorithms, particularly those using unsupervised learning, can be unleashed on vast datasets with minimal instructions. Instead of being told to find a specific type of signal, they are simply tasked with finding anything that is anomalous, anything that stands out from the natural background in a statistically significant way. This technique could uncover signals that are compressed, encrypted, or modulated in ways that are completely alien to our understanding of information theory. An AI doesn't need to understand the message, it just needs to recognize that the pattern is artificial. It could find a signal that looks like random noise to our eyes but contains a complex, non-natural structure invisible to conventional analysis. This shifts the search from a targeted hunt for something we expect to an open-minded exploration for anything that is unexpected, dramatically widening the net we cast into the cosmic ocean and offering our best chance of finding a signal that doesn't play by our preconceived rules. From the fleeting, tantalizing shout of the wow signal to the clockwork rhythm of a repeating fast radio burst, from the impossible dimming of a distant star to the ghostly currents of the dark flow, our journey through these 25 enigmatic signals has been a tour of the very frontiers of human knowledge. We have stood alongside astronomers as they've circled a single, shocking line of data in red pen, and we felt the collective thrill of a global scientific community mobilizing to investigate a potential hello from a sun-like star. We've encountered phantom signals from faulty kitchen appliances and witnessed the profound humility of scientists debunking their own most exciting discoveries. Each signal, whether ultimately explained by a comet's destruction, a magnetar's tantrum, or a satellite's errant transmission, represents something far greater than itself. They are individual brushstrokes in a much larger portrait of our species' relentless, awe-inspiring quest to understand the cosmos and our place within it. This grand investigation plays out in the constant, dynamic tension between two powerful ideas. On one hand, we have the disciplined, rigorous application of Occam's razor, the principle that the simplest, most natural explanation is usually the correct one. This scientific skepticism is our essential filter, the tool that has saved us from countless false alarms and kept our feet firmly on the ground. It is the process that identified the Ross 128 signal as satellite interference and revealed the Puritans as an impatient astronomer's microwave. Yet, on the other hand, we hold onto the breathtaking, expansive possibility that the universe might be home to other conscious beings. This hope is the engine of curiosity, the force that drives us to build ever more sensitive telescopes and to dream of what might be. The true wonder is that both of these impulses are necessary. Skepticism without imagination is a dead end. Wonder without rigor is just fantasy. It is in the delicate, productive balance between them that real discovery is made, whether that discovery is a new type of pulsar or simply a better understanding of our own technological clutter. What becomes abundantly clear is that the universe is vastly more creative and violent than we could have ever conceived from our quiet little planet. The signals we've explored are not anomalies in an otherwise calm and predictable cosmos. They are the unmistakable signs of a universe in a constant state of ferocious transformation. Stars are being torn apart by black holes, neutron stars are cracking their crusts in starquakes, and entire galaxies are billowing with the energy of ancient cataclysms. The cosmos is not a quiet museum. It is a living, breathing, and often terrifyingly beautiful arena of extreme physics. The fact that we have developed the technology to eavesdrop on this cosmic drama, to detect the faint whispers of events occurring billions of light years away, is one of the greatest achievements in human history. So where does this leave us, the curious inhabitants of a pale blue dot surrounded by all this mystery? It leaves us exactly where we have always been, as perpetual students of the sky, our noses pressed against the glass of the cosmic window, yearning to see more. The search itself is the point. The act of listening, of questioning, of tirelessly trying to decipher the universe's coded messages is a profound expression of what it means to be human. Every unexplained signal is not a failure of understanding, but an invitation, a promise that there is still so much more to learn, to discover, and to wonder about. These 25 signals are not a closed list, they are an opening chapter. New mysteries are being detected every day, each one waiting for its own story to be told. So keep looking up, stay curious, question everything, and listen closely, for the universe is still whispering, and its greatest secrets are yet to be revealed. But as our journey through these 25 cosmic mysteries comes to a close, I want to turn the microphone over to you. Which of these enigmatic signals captured your imagination the most? Was it the fleeting, perfect mystery of the wow signal, a single shout in the dark that has never been repeated? Or perhaps the baffling, structured rhythm of FRB 180916, the cosmic alarm clock that defies easy explanation? Maybe it's the haunting possibility of the dark flow, a ghostly current hinting at realms beyond our observable universe, or the tantalizing, albeit debunked, story of Oumuamua that has you questioning what might be sailing between the stars. Let me know your favorite down in the comments below. I read every single one, and I'm genuinely fascinated to hear which cosmic puzzle resonates with you. If this exploration into the universe's deepest secrets sparked your curiosity, then you're in the right place. Consider subscribing to the channel and hitting that notification bell, because this is just the beginning. We have so many more cosmic journeys planned, from diving deeper into the science of black holes and neutron stars to exploring the latest, jaw-dropping discoveries from the James Webb Space Telescope. The universe is an endless source of wonder, and together we'll continue to unravel its stories one mystery at a time. And as you go about your day, I'll leave you with this final thought to ponder. We've seen that the cosmos is far from silent. It is a symphony of strange and powerful signals, each one a question waiting for an answer. With powerful new tools like the Square Kilometre Array coming online and advanced artificial intelligence sifting through the data, we are on the cusp of a new era of discovery. The next great cosmic revelation could be just moments away. What will we find next? Will it be a definitive signal from another civilization, finally answering the ancient question of whether we are alone? Or will it be something entirely unforeseen, a new class of phenomenon that challenges our understanding of physics itself? The greatest enigmas are still out there, waiting for the right moment and the right observer to be understood. The universe has been whispering its secrets for billions of years. We are only just beginning